settle in. Dim the lights if you've got them on, pull the blanket up, and let your shoulders drop an inch or two, because tonight we're asking a question that sounds almost rude to a physicist. Did the Big Bang actually happen? It's a strange thing to even ask. Most of us grew up with the idea baked in, the way we grew up knowing the Earth orbits the sun. A long time ago, everything was packed into a single point, it banged, and 13.8 billion years later, here we are lying in bed wondering about it. Case closed, right? Not quite. Because if you actually corner a cosmologist at a conference and ask them plainly, did it happen? They won't give you a simple yes. They'll pause. They'll get that look. And then they'll start talking about evidence, about models, about the difference between a theory that's been tested 1,000 times and a theory that's been proven beyond all possible doubt. Because in science, those are not the same thing. So tonight, we're not going to just recite the standard story and call it settled. We're going to actually interrogate it. We're going to ask what the evidence really shows, where it's airtight, where it gets shaky, and where serious scientists still argue late into the night at university bars about whether we've got this whole origin story right. By the end, you'll understand not just what the Big Bang Theory says, but why we believe it, how confident we should really be, and what it would even mean if it turned out to be wrong. Before we start drifting, I'd love to know where you're tucking in from tonight. Drop it in the comments before your eyes get too heavy to type. And if this is your first time settling in with us, consider subscribing. These slow, curious deep dives come out regularly, and it helps more sleepy minds find their way here. If you're already part of this little nighttime audience, thank you for coming back. Now, let's get comfortable and ask the question properly. A name that was never supposed to stick. Here's the first wrinkle in this story, and it's a fun one. The name Big Bang was invented as an insult. In 1949, a British astronomer named Fred Hoyle was on the radio, and he didn't actually believe in the expanding universe model that's now the standard picture. He was a strong supporter of a rival idea. We'll get to it later tonight. And during his broadcast, he referred to the competing theory dismissively as this Big Bang idea. He meant it to sound a little silly, a little crude. Instead, the phrase escaped into the wild, took on a life of its own, and somehow ended up as the official name for the most successful cosmological model in the history of science. Hoyle, ironically, helped brand the very idea he spent his career fighting against. That history matters because it tells you something important right away. The name suggests an explosion, a fireball, a bang in the traditional sense, with a center and an edge and a moment you could stand outside of and watch. None of that is actually what the theory describes. There was no detonation in empty space. There was no center. There was no outside from which to witness it. What the theory actually proposes is something stranger and, honestly, harder to picture. That space itself, the literal fabric that separates one point in the universe from another, has been stretching since the very beginning, carrying galaxies along with it like specks of pepper scattered across the surface of a balloon as someone blows it up. The pepper isn't moving across the rubber. The rubber is expanding underneath it. So when we ask, did the Big Bang happen? We have to be precise about what we're even asking. Are we asking whether space has been expanding for billions of years? Are we asking whether the universe had an absolute beginning, a true 0 point? Are we asking whether we understand the first fraction of a second after that 0 point? Because those are three very different questions, and they have three very different levels of certainty attached to them. Let's take them one at a time. Starting with the part of the story that's on the firmest ground of all. The galaxies are running away from us, and that's not a metaphor. In the early 20th century, astronomers pointed their telescopes at faint, fuzzy patches of light they called spiral nebulae, what we now know to be entire galaxies full of hundreds of billions of stars sitting unimaginably far from our own. They split that light apart using prisms, expecting a rainbow scatter of colors, different signatures from different chemical elements. What they found instead was oddly consistent. Each galaxy showed the same familiar patterns of light you'd expect from hydrogen, from helium, from the basic elements we know well. But those patterns weren't sitting where they were supposed to. They were all shifted toward the red end of the spectrum, as if every single galaxy's light had been stretched out on its way to Earth. An American astronomer named Edwin Hubble, building on calculations from a Belgian priest and physicist named Georges Lemaitre, noticed something even stranger buried in that pattern. The farther away a galaxy was, the more its light had been stretched. Not randomly, proportionally. A galaxy twice as far away showed roughly twice the shift. That clean linear relationship is now called the Hubble-Lemaitre law, and it remains one of the most reproduced results in all of astrophysics. Here's the part that trips people up. This doesn't mean galaxies are firing through space like cosmic bullets, racing away from some central explosion. If you really were watching shrapnel fly outward from a blast, the universe would have an obvious center, the point of detonation, and we'd expect to be sitting somewhere off to one side of it. But that's not what we observe. No matter which direction we look, galaxies appear to be moving away from us, and the math says an observer in any other galaxy would see the exact same thing from their vantage point. Every observer seems to sit at the middle of their own expanding bubble. The honest explanation isn't an explosion at all. It's that the space between galaxies is growing. Picture dough with raisins scattered through it, rising in the oven. Every raisin watches every other raisin drift farther away. Not because the raisins are swimming through the dough, but because the dough itself is expanding everywhere at once, uniformly, with no center and no edge. This single observation, galaxies receding in proportion to their distance, is about as solid as evidence gets in science. It's been confirmed with completely different instruments, different teams, different decades of technology, and it keeps coming back the same. If you're asking, did space expand, the data answers with about as resounding a yes as cosmology ever offers. But notice what this evidence does not tell us. It tells us the universe is bigger today than it was yesterday and was smaller yesterday than it will be tomorrow. Run the expansion backward in your head, and you arrive at a moment when everything was scrunched far closer together. It does not, by itself, prove there was a single infinitely dense starting point, or tell us what physics governed that moment, or even guarantee that rewinding all the way to zero is mathematically valid rather than a breakdown of the equations. That distinction, expansion versus an actual singular beginning, is exactly the kind of nuance that gets flattened when people summarize the Big Bang in a single breathless sentence. The photograph nobody was looking for. If shifting starlight were the only evidence on the table, you could maybe argue the case wasn't fully closed. Skeptics in the mid-20th century certainly tried. But then, in 1965, something happened that turned a strong hypothesis into something much closer to an established fact. Two radio engineers in New Jersey, Arno Penzias and Robert Wilson, were testing an enormous horn-shaped antenna meant for satellite communication. No matter what they did, they kept picking up a faint, irritating hiss of background noise, the same in every direction, day and night, summer and winter. They checked the wiring. They checked for interference from nearby cities. They even climbed into the antenna and scraped out what they politely called pigeon droppings, suspecting the birds nesting inside were somehow responsible. The hiss remained. What they didn't know, at first, was that just 30 miles away, a team of physicists at Princeton had been building an experiment specifically designed to detect a relic signal predicted by the expanding universe model. The leftover glow from a much hotter, denser early universe, cooled by billions of years of expansion into the microwave part of the spectrum. When the two groups connected the dots, it became clear that Penzias and Wilson's stubborn noise wasn't noise at all. It was the oldest light in existence, arriving from every direction in the sky, exactly as theory had predicted decades earlier. This is the cosmic microwave background, and it deserves to be taken seriously as evidence precisely because it wasn't found by people looking to confirm a theory they liked. It was found by accident, by engineers trying to get rid of static, and it matched a specific quantitative prediction that had been made years in advance. That's about as close as cosmology gets to a smoking gun. Here's the physical picture behind it. Roughly 380,000 years after the universe's earliest moments, the cosmos was an opaque, glowing plasma. Protons, electrons, and photons all jammed together so tightly that light couldn't travel more than a short distance before smashing into a charged particle and scattering off in a new direction. It would have been like trying to see through the inside of a thundercloud. Light existed, but it couldn't go anywhere useful. As the universe expanded, it cooled. And there's a specific temperature, around 3,000 degrees, where something elegant happens. Electrons slow down enough to be captured by atomic nuclei, forming neutral atoms for the first time. Once those free electrons were swept up, there was nothing left for photons to keep bouncing off of. Light, almost overnight in cosmic terms, became free to travel in straight lines across the universe. Those very photons, the ones that broke free at that moment, are still arriving today, stretched by more than 13 billion years of cosmic expansion. What was once a blinding, searing glow has been drawn out into faint microwave radiation, hovering at just under 3 degrees above absolute zero, filling every cubic inch of space, including the room you're lying in right now. About 1% of the static you'd see on an old unplugged television antenna was this very light, completing a 13 billion year journey, just to end its trip as a flicker of noise on your screen. Later missions made this picture almost absurdly precise. NASA's COBE satellite in 1989 confirmed that this background radiation follows almost exactly the spectrum you'd expect from a cooling, glowing object, a result so clean it won its discoverers a Nobel Prize. The WMAP mission in the 2000s, and later the European Planck satellite, mapped out tiny temperature variations across this ancient light, differences of only a few millionths of a degree, and used them to pin down the universe's age at roughly 13.8 billion years. Its geometry is remarkably flat, and its composition down to precise percentages of ordinary matter, and dark energy. So if the question is there a leftover glow from an early hot, dense phase of the universe? The answer, again, is about as confidently yes as physics allows. This is not a single ambiguous data point. It's a detailed, textured signal that has been measured, remeasured, and cross-checked by multiple independent space missions using entirely different instruments. And it keeps matching the predictions made by the expanding universe model with extraordinary precision. The universe's first and only cooking show. There's a third leg holding this whole picture up, and it's arguably the most quietly impressive of the three because it involves chemistry rather than just light. In the first few minutes after the universe's earliest moments, somewhere between about 1 second and 20 minutes in, conditions were hot enough and dense enough for protons and neutrons to start fusing together into the simplest atomic nuclei. This brief window is called primordial nucleosynthesis, and it's essentially the only cosmic-scale chemistry experiment the universe ever ran without the help of stars. The math here is unforgiving in a useful way. Physicists can calculate, using nothing but well-tested nuclear physics from laboratories right here on Earth, exactly what ratio of hydrogen to helium to trace amounts of deuterium and lithium-7 should have been produced during those frantic first minutes, given how fast the universe was expanding and cooling. The prediction comes out to roughly 75% hydrogen, 25% helium by mass, with only the faintest whisper of heavier light elements. When astronomers go looking for the most pristine, least contaminated gas clouds in the universe, pockets of material that have never been touched by a star's fusion furnace, they find almost exactly that ratio. Not roughly in the ballpark, startlingly close, across multiple independent elements, all measured by completely different techniques. This matters enormously for our central question, because this isn't a single measurement that could be a fluke or a coincidence. It's a prediction made from particle physics, tested against astronomical observation, and the two completely separate fields agree with each other to a remarkable degree. If the early universe hadn't actually been hot and dense in the way the Big Bang model describes, there's no good reason these numbers should line up. The fact that they do is what scientists call independent corroboration, separate lines of evidence built on separate assumptions, converging on the same story. There is one persistent wrinkle worth mentioning honestly, because pretending the model is flawless would be dishonest. The predicted abundance of lithium-7 doesn't quite match what we observe in the oldest stars. It's off by a noticeable margin, a puzzle cosmologists affectionately call the lithium problem. Nobody is certain whether this points to some subtle process altering lithium inside ancient stars after the fact, some small gap in our understanding of the early universe, or something more interesting we haven't figured out yet. It's a real discrepancy, and it's one of the genuine cracks in an otherwise startlingly consistent picture. Exactly the kind of detail that keeps the question, did the Big Bang happen, from being a closed book rather than an open and ongoing investigation. Three witnesses telling the same story step back for a second and look at what we've actually got. Three completely different kinds of evidence: the stretching of galaxy light, the leftover glow of ancient radiation, and the precise chemical recipe of the early universe. Were discovered using different instruments, by different teams, often decades apart, and none of them were designed to simply confirm what the others had already found. Yet they all converge on the same underlying picture: a universe that was once far smaller, far hotter, and far denser than it is now, and has been expanding and cooling ever since. In courtroom terms, this is the difference between a single eyewitness and three unrelated witnesses with no contact with each other, all independently describing the same event in matching detail. That's a strong case. It's the reason the Big Bang model isn't just the popular opinion among cosmologists. It's the model that keeps surviving every new test thrown at it, including tests designed specifically to break it. So why would anyone still ask, seriously, whether it happened, where the confidence actually runs out? Here's where things get genuinely interesting, and where the question in tonight's title stops being rhetorical and starts being a real, live conversation happening in physics departments right now. The evidence we just walked through is extraordinarily strong for describing the universe from roughly 1 second after its beginning onward. Scientists sometimes call this the well-tested Big Bang. The parts you can actually trace using known physics, tested in particle accelerators, confirmed by direct observation. That part of the story is on rock-solid footing. But push earlier than 1 second, and the ground gets considerably softer. Push back to the very first fraction of a second, the so-called Planck era, lasting less than a trillionth of a trillionth of a trillionth of a second. And our best theories simply stop working. At those scales, gravity and quantum mechanics, our two most successful frameworks in all of physics, are required to operate together, and we don't yet have a working theory that lets them. General relativity describes gravity beautifully at large scales, but breaks down into mathematical nonsense, infinities, contradictions, when you try to apply it to a single point of infinite density. Quantum mechanics describes the tiny and the probabilistic beautifully, but has never been successfully merged with gravity into one complete framework. This is not a minor technical footnote. It means that when people picture the Big Bang as a single instant where literally everything sprang from an infinitely small, infinitely dense point, they're describing something our current physics can't actually verify and, in a strict mathematical sense, can't even properly define. The singularity at the very beginning isn't a confirmed physical event. It's the point where our equations throw up their hands and say, we don't know what happens here. So if your question is, did everything begin from a literal, infinitely dense point? The honest scientific answer is, we don't actually know that, and many physicists suspect it's probably not literally true, but rather a sign that we need a better theory, something like quantum gravity, to describe what really happened at the very beginning. The singularity might be a mathematical illusion created by pushing a theory past the point where it's valid, the same way Newton's equations of gravity start producing strange answers if you push them to describe the orbit of Mercury too precisely, eventually requiring Einstein's relativity to correct them. This is one of the most important things to understand about the Big Bang model. It is not technically a theory about the absolute beginning of everything. It's a theory about how the universe evolved from an extremely hot, dense early state. Whether there was a true 0 point, an actual moment of absolute beginning, is a separate and much harder question that current physics genuinely cannot answer with confidence. The inflation problem, a patch that works suspiciously well. There's a second place where the standard story gets shakier, and it involves an idea called cosmic inflation. When scientists first worked out the details of the early expanding universe, they ran into a few stubborn puzzles. The cosmic microwave background, that ancient leftover light, turns out to be almost perfectly uniform in temperature across the entire sky, varying by only millionths of a degree. The problem is that opposite sides of the observable skies are so far apart that, under standard expansion alone, there hasn't been enough time since the beginning for heat or light to have traveled between them and equalized their temperatures. It's as if two bakers on opposite sides of the planet, who've never communicated, ended up with identical recipes down to the gram. That's called the horizon problem. There's also the flatness problem. The geometry of the universe, as best we can measure it, is remarkably close to flat, meaning parallel lines stay parallel across cosmic distances rather than curving like they would on the surface of a sphere or a saddle. But flatness is mathematically unstable. If the early universe had been even slightly curved, that curvature should have been dramatically amplified over billions of years of expansion, like a small wobble getting magnified the longer a spinning top spins. The fact that the universe is still nearly flat today implies it must have started out flat to an almost absurd degree of precision. Why would that be? And there's the monopole problem. Certain respected theories of particle physics predict that the early universe should have produced large numbers of exotic particles called magnetic monopoles. We have never found a single one anywhere, despite decades of dedicated searching. In the early 1980s, physicist Alan Guth proposed a fix for all three puzzles at once, a period of unimaginably fast expansion happening in a sliver of a second, during which the universe ballooned in size by a staggering factor, potentially by a factor of 10, followed by 70 zeros, before settling back into the more familiar, gentler expansion we observe today. This burst, called inflation, would stretch regions that were once close enough to share the same temperature out to enormous distances, explaining the uniformity. It would flatten out any initial curvature, the same way blowing up a balloon makes its surface look locally flatter and flatter. And it would dilute any monopoles down to such a low density that we'd essentially never expect to find one in our observable patch of sky. Inflation is elegant. It solves three separate problems with one mechanism, and it makes a testable prediction. Tiny quantum fluctuations, stretched out by inflation into the seeds of all future galaxies, should leave a specific statistical fingerprint in the cosmic microwave background. When satellites like WMAP and Planck measured that fingerprint, it matched what inflation predicted with impressive accuracy. But here's the honest caveat, the one that doesn't always make it into the confident summary version of this story. Inflation is a model bolted onto the Big Bang framework to fix problems the original framework couldn't solve on its own. And we still don't know exactly what physical stuff drove it. Physicists describe it using something called an inflaton field, but this field has never been directly detected. It's inferred entirely from the patterns it would have left behind, not observed directly in any laboratory. Multiple competing versions of inflation exist, making slightly different predictions and narrowing down which version, if any, actually happened is an active and unresolved area of research. Some physicists have raised more fundamental concerns, arguing that certain versions of inflation are so flexible they could explain almost any observation, which makes them harder to definitively test or rule out. A property that makes some scientists uneasy, because a theory that can explain anything risks explaining nothing in particular. So when someone asks, did the Big Bang happen, and you dig into the inflation chapter specifically, the honest answer shifts from yes, overwhelmingly, to very probably. And the evidence is genuinely compelling, but this particular piece of the puzzle is still being actively debated and refined by the people closest to the data. The tension nobody can quite resolve. There's a third crack worth sitting with tonight, and it's not about the deep ancient past at all. It's about right now, this very moment, and it has a name: the Hubble tension. Remember that number, the Hubble constant, that tells us how fast the universe is expanding today. You'd think there'd be one agreed upon value. There isn't. If you calculate it by carefully measuring the cosmic microwave background and working forward through the standard model of cosmology, you get one number, close to 67 kilometers per second for every roughly 3 million light-year stretch of space. If you instead measure it directly, using nearby pulsing stars and exploding stars to build a ladder of cosmic distances and clock how fast galaxies are receding right now, you get a noticeably different number, closer to 74. Both methods have been refined for decades. Both have been cross-checked by multiple independent teams using different telescopes and different techniques. And they still don't agree, with a gap too large to easily explain away as simple measurement error anymore. This is not a minor academic squabble. It's a persistent, statistically significant disagreement between two of the most carefully measured numbers in all of cosmology. And right now, nobody knows for certain whether it points to a flaw somewhere in our distance measuring techniques that hasn't yet been found, despite years of searching. A gap in the standard cosmological model itself, meaning our equations for how dark energy and the universe's contents behave, might need a correction we haven't identified yet, or genuinely new physics. Some unknown ingredient or process in the early universe that we haven't accounted for at all. This tension doesn't threaten the broad outline of the Big Bang story. Nobody studying the Hubble tension thinks the universe didn't expand from a hot, dense state. But it's a vivid, current reminder that even our best-tested cosmological framework has an open wound in it, a place where the model doesn't yet fully agree with itself, depending on how you choose to measure it. That's not the sign of a dead, finished theory. It's the sign of a living one, still being pressure-tested by people who refuse to look away from an inconvenient number. The competing stories we almost believed instead. It's worth remembering, too, that the Big Bang model was never the only option on the table, and treating it as some kind of automatic, obvious conclusion erases just how hard-fought its acceptance actually was. In 1948, the same year cosmic expansion was already gaining traction, three physicists, Fred Hoyle, Hermann Bondi, and Thomas Gold, proposed an entirely different picture called the steady-state theory. In their model, the universe genuinely had no beginning and no end. Yes, galaxies were observed to be moving apart, they conceded that much. But in their version, new matter would continuously and gently pop into existence in the gaps between galaxies, keeping the overall density of the universe constant forever. No fiery start, no awkward question of what came before, just an eternal, self-renewing cosmos. For years, this was a serious scientific rival, not a fringe idea. It made its own testable predictions, and it had real defenders among respected physicists. What ultimately broke it wasn't philosophical preference. It was that 1965 discovery of the cosmic microwave background. The steady-state model had no good way to explain a uniform, ancient glow filling the entire sky. The expanding hot Big Bang model had predicted almost exactly that signal years in advance. When the evidence came in, it favored one model clearly and specifically, and the scientific community, however reluctantly in some corners, followed the data. That history should make us a little humbler about declaring any current model permanently settled. Other alternatives have continued to be explored since then, and they're worth knowing about, because they show this isn't a closed debate so much as an active frontier with its edges still being mapped. Some physicists have explored cyclic or bouncing universe models, where our expansion phase was preceded not by a singularity but by a previous contracting universe that reached an extremely dense state and then rebounded outward, possibly as part of an endless cycle of expansion and contraction repeating forever. Other versions, inspired by string theory, imagine our Big Bang as the result of a collision between higher dimensional structures called branes, with our familiar three-dimensional universe being just one slice of something far larger and stranger. Still others work within quantum cosmology, attempting to describe the universe's birth not as a singular event in time at all, but as some kind of quantum transition from a prior state where the very concepts of before and after may not have applied in any way we'd recognize. None of these alternatives currently explain the observational evidence, the expansion, the microwave background, the light element abundances, better than the standard model does. That's an important, often overlooked point. It's not that scientists are choosing the Big Bang model out of habit or convention. It's that every serious rival proposed so far has either failed to match the data as precisely or hasn't yet produced testable predictions specific enough to compare against the data at all. But these alternatives remain active research programs, not historical curiosities, which tells you something important. The broad strokes of the story, an early, hot, dense, expanding universe, are about as well established as anything in cosmology gets. The fine print about what triggered it, what came before it, and what was happening in that first unimaginably brief instant remains genuinely, actively unresolved, the stuff we can't see and can't quite explain. There's one more honest complication worth including before we wind toward sleep, because it would be a disservice to pretend the standard cosmological model is a tidy, fully explained system. Roughly 95% of the universe's total content, by current estimates, is made of two ingredients we cannot directly see, cannot directly touch, and do not fully understand. About 27% is dark matter, inferred not because we've detected it directly, but because galaxies rotate as if vastly more mass is holding them together than we can account for with visible stars and gas alone, because clusters of galaxies bend background light through gravity far more strongly than their visible matter should allow. And because the patterns in the cosmic microwave background only make sense mathematically if you include this invisible gravitational scaffolding in the model. Multiple completely independent lines of evidence point to something there. But despite decades of dedicated, sensitive underground experiments designed to catch a direct interaction, no dark matter particle has ever been definitively detected in a laboratory. About 68% is dark energy, an even stranger ingredient, inferred from the discovery in the late 1990s that the universe's expansion isn't just continuing, it's accelerating, speeding up rather than gradually slowing under gravity's pull, as most physicists had expected. Something is pushing space apart with increasing strength, and we genuinely do not know what that something is. It might be an inherent property of empty space itself, a kind of built-in cosmic pressure. It might be something that changes over time in ways we haven't detected yet. It might require an adjustment to gravity itself on the largest scales. Honestly, right now, nobody knows. This means that the standard cosmological model, the one that explains expansion, the microwave background, and the light element abundances so convincingly, only works at all if you accept that the vast majority of the universe is made of two things we cannot directly observe and do not understand at a fundamental level. That's not a minor footnote. It's arguably the biggest open question in modern physics, sitting right at the center of the model we're discussing tonight. How big is everything, anyway? Before we go further into the cracks, let's pause on something that trips up almost everyone the first time they really think about it, because it changes the whole shape of tonight's question. When people say the universe, they usually picture the totality of existence. But when cosmologists say it, they often mean something narrower and more honest: the observable universe, the portion we can actually see and measure. Light travels fast, but not infinitely fast. It moves at roughly 300,000 kilometers every second, and the universe has only existed for a finite stretch of time, about 13.8 billion years. So there's a hard limit on how far any signal could have traveled to reach us. Multiply the speed of light by the age of the universe, account for the fact that space itself has been stretching the entire time those photons were in transit, and you get a sphere centered on Earth, roughly 93 billion light-years across. That's our observable universe. Beyond its edge lies a horizon we cannot see past, not because there's nothing there, but because light from that far away simply hasn't had time to reach us yet. This matters enormously for our central question, because the entire evidentiary case we just walked through, the redshift, the microwave background, the light element ratios, only describes this observable patch. The actual universe, the whole of it, could be vastly larger. It might be infinite. It might loop back on itself in some exotic geometric way we haven't detected. It might contain regions completely cut off from us forever by the sheer scale of cosmic distance. So when someone asks, did the Big Bang happen, there's a quiet but important qualification buried in any honest answer. We can only really speak with confidence about the patch of cosmos we can actually observe. The Big Bang model describes how that patch behaved. Whether the same story applies uniformly to the rest of an unobservable, perhaps infinite universe is, strictly speaking, an extrapolation, a reasonable and well-motivated one, but an extrapolation nonetheless. It's a little like being handed one drop of water from an ocean you cannot see the edges of, testing it thoroughly, and then reasoning, carefully and with good cause, that the rest of the ocean probably behaves the same way. Probably, not provably. The cosmic distance ladder and why measuring the universe is harder than it sounds. Almost everything we've discussed tonight depends on astronomers being able to measure distance accurately, and it's worth slowing down on just how difficult that actually is, because the difficulty itself is part of why some of these debates, like the Hubble tension, remain unresolved. You cannot simply point a tape measure at a galaxy. Instead, astronomers built what's affectionately known as the cosmic distance ladder, a chain of overlapping techniques, each one calibrated against the rung below it, climbing higher and higher into the depths of space. The first rung relies on nearby stars called Cepheid variables, stars that pulse rhythmically, brightening and dimming on a predictable schedule. Remarkably, the speed of that pulse is directly tied to the star's true brightness. Once you know how bright a star actually is, you can compare that to how dim it appears in the sky and calculate its distance. The same way you could estimate how far away a candle is if you already knew its exact wattage. Hubble used Cepheids in nearby galaxies to anchor the lowest rungs of his ladder back in the 1920s, and astronomers still use them today, just with vastly more sensitive instruments. Once you climb past the distance where individual stars become too faint to resolve, astronomers switch to brighter, rarer events called standard candles. The most famous of these are Type Ia supernovae, the catastrophic explosions of collapsing white dwarf stars. These explosions are so consistent in their intrinsic brightness that they function as reliable cosmic light bulbs of known wattage, visible across billions of light years. Compare their expected brightness to their observed brightness, and you've got a distance. Combine that distance with how much their light has been redshifted, and you've got both a ruler and a speedometer in a single measurement. Each rung of this ladder introduces its own small uncertainties, its own assumptions, its own potential sources of error, from interstellar dust dimming starlight unevenly to subtle differences in stellar chemistry that might quietly bias the calibration. None of these uncertainties are fatal on their own, and when independent methods converge on similar numbers, confidence grows. But it's exactly this kind of layered, ladder-built measurement that lies underneath the disagreement in the Hubble tension we discussed earlier. A tiny systematic bias introduced on a lower rung could, in principle, ripple upward and throw off everything built on top of it. Untangling whether that's actually happening or whether something deeper and more interesting is going on is one of the most active detective stories in modern astrophysics, catching the universe bending light. There's another, quieter kind of evidence worth knowing about tonight because it doesn't rely on distance ladders or ancient radiation at all. It relies on gravity bending light itself, exactly as Einstein's general relativity predicted more than a century ago. When light from a distant galaxy passes near a massive foreground object, like a giant cluster of galaxies, the path of that light gets bent by the gravity of everything sitting in its way. From our vantage point, the background galaxy's image can appear smeared into an arc, duplicated into multiple images, or magnified far beyond its normal brightness. This effect, called gravitational lensing, isn't subtle once you know to look for it. Some of the most striking images ever captured by modern telescopes show glowing arcs of light curling around the edges of massive galaxy clusters. The visual fingerprint of mass warping the space light travels through. What makes this useful for tonight's question is that lensing lets astronomers map out where mass actually sits in the universe, independent of whether that mass glows or not. And when scientists tally up how much bending is actually occurring, the numbers consistently demand far more mass than we can account for with visible stars and gas. That mismatch is one of the strongest independent lines of evidence for dark matter, sitting completely apart from the galaxy rotation arguments and the microwave background arguments we'll get to shortly. Three unrelated methods, again, converging on the same uncomfortable conclusion. Most of the universe's mass is invisible to us. Lensing also offers a second, subtler tool. By studying how the pattern of bending changes at different cosmic distances, astronomers can trace how matter has clumped together over billions of years of cosmic history, providing yet another independent check on the expansion rate and the overall structure of the cosmos. It's a completely different kind of measurement from supernova brightness or microwave background ripples, built on different physics entirely. And it keeps landing in roughly the same neighborhood as the rest of the evidence. That kind of cross, from totally unrelated angles, is exactly the sort of thing that builds genuine scientific confidence rather than mere consensus. The sound waves frozen into the sky. There's one more measuring tool worth understanding, because it sounds almost too strange to be real. Astronomers can measure the size of literal sound waves that rippled through the universe when it was less than 400,000 years old. And those frozen sound waves are still etched into the positions of galaxies today. Before the cosmic microwave background was released, the early universe was a hot, dense plasma where matter and radiation were tightly coupled together, pushing and pulling against each other. Regions that were slightly denser than average compressed under their own gravity, then rebounded outward as radiation pressure pushed back, creating actual pressure waves rippling outward through the plasma, not unlike sound moving through air. When the universe cooled enough for atoms to form and light to break free, those waves froze in place, leaving behind a preferred separation distance between regions of slightly higher density, roughly 500 million light-years across. That preferred space, called a baryon acoustic oscillation, still shows up faintly in how galaxies are distributed across the sky today, billions of years later. By measuring that spacing at different points in cosmic history, astronomers get an independent yardstick for tracking how the universe's expansion rate has changed over time a yardstick built on entirely different physics than supernova brightness or microwave background mapping. When you put baryon acoustic oscillations, gravitational lensing, supernova distances, and the cosmic microwave background all on the same chart, plotted against each other, they line up with remarkable consistency, except for that stubborn Hubble tension we already discussed. Four separate techniques built on four separate physical principles, largely agreeing with one another, is not the kind of agreement you'd expect from a model that was fundamentally broken. It's the kind of agreement you'd expect from a model that's mostly right, with one or two details still waiting to be worked out. The particle that refuses to be caught. Let's go back to one of the universe's shyest characters for a moment, because it's a perfect example of evidence that supports the standard cosmological story without ever being directly observed, which is exactly the kind of nuance worth sitting with tonight. In the first second after the universe's earliest moments, neutrinos, ghostly particles that barely interact with anything at all, were swimming through the hot plasma just like everything else. But because they interact so weakly, they decoupled from the rest of matter almost immediately, far earlier than the photons that would eventually become the cosmic microwave background. From that moment on, these primordial neutrinos have been streaming freely through space, cooling as the universe expands, and should now form their own ancient relic radiation, a cosmic neutrino background, slightly older and even fainter than the microwave background. Nobody has ever directly detected this neutrino background. The interaction is simply too weak for any current detector to register it. And yet, cosmologists are confident it exists, not because they've seen it, but because the universe behaves as though it's there. When physicists build detailed models of how fast the early universe expanded, how matter clumped together, and exactly what pattern of ripples should appear in the cosmic microwave background, those models only match observations if a cosmic neutrino background is included in the calculation. Leave it out, and the predicted patterns shift in ways that don't match what telescopes actually record. Put it back in, and the numbers snap into place. This is worth pointing out because it's a clean example of how much of modern cosmology works, not through direct observation of every single piece, but through a web of consistent, interlocking predictions where removing any one piece causes the whole structure to stop matching reality. It's indirect evidence, yes, but it's the same kind of indirect evidence that let physicists confidently predict the existence of the neutrino itself decades before it was ever caught in a laboratory in 1956. Indirect doesn't mean weak. It means we're inferring something we can't directly touch from its consistent fingerprints on everything around it, which is, frankly, how an enormous amount of real science actually works. The coin flip that built everything. There's a puzzle sitting quietly underneath this entire story, one so strange that it's almost easy to forget, because without its resolution, none of the rest of tonight's discussion would even be possible. According to the physics we understand, the extremely early universe should have produced matter and antimatter in exactly equal amounts. Every particle should have had its mirror image antiparticle, and whenever matter and antimatter meet, they annihilate each other completely, converting entirely into pure radiation. If that had played out with perfect symmetry, the early universe should have annihilated itself almost instantly, leaving behind nothing but a uniform bath of light. No atoms, no stars, no galaxies, no you. But that obviously isn't what happened. Everything you can see, every star, every planet, every living thing, is made of matter, with essentially no naturally occurring antimatter anywhere to be found. Somewhere in those earliest moments, nature apparently preferred matter over antimatter by a startlingly tiny margin. Something on the order of one extra matter particle for every billion matched pairs that destroyed each other. That razor-thin surplus is the entire reason there's a universe full of stuff instead of an empty bath of leftover light. We don't fully understand why that asymmetry exists. In 1967, the physicist Andrei Sakharov laid out 3 conditions any explanation would need to satisfy, and physicists have spent more than half a century since trying to find a mechanism that actually fulfills all 3 convincingly. We've observed hints of the right kind of asymmetry in laboratory experiments involving certain exotic particle decays, but the amount we've measured directly is far too small to account for the dramatic imbalance the universe actually shows. Something bigger is going on, and we don't yet know what. This is, again, exactly the kind of honest gap worth including tonight. The standard cosmological story requires this asymmetry to exist in order for any of the rest of the narrative. Stars, galaxies, the very atoms making up your bookshelf. To make sense, we know the asymmetry happened because we're here to ask about it. We just don't yet have a confirmed mechanism explaining why, which means there's a genuinely unsolved piece of physics sitting at the very foundation of the standard story, hiding in plain sight, building galaxies out of nearly nothing. Once the fog of the early plasma cleared, and that ancient light broke free, the universe entered a long, dark stretch, sometimes called the cosmic dark ages, hundreds of millions of years, with no stars, no galaxies, nothing but cooling clouds of hydrogen and helium gas drifting under the patient pull of gravity. Eventually, in regions that happened to be just slightly denser than their surroundings, gravity won out, gas collapsed inward, temperatures climbed, and the very first generation of stars ignited. These first stars, sometimes called population 3 stars, would have been almost unrecognizable compared to anything shining today, forming from gas with no heavier elements at all to help it cool and fragment efficiently. That primordial gas tended to collapse into a small number of enormous clumps rather than splitting into many smaller stars the way gas clouds do today. Simulations suggest some of these first stars may have been hundreds of times more massive than our sun, burning ferociously hot and living extraordinarily short lives, sometimes just a few million years, before exploding or collapsing into early black holes. When those first stars died, many in spectacular explosions, they scattered the first heavier elements ever created into the surroundings, gas, carbon, oxygen, and beyond, the raw ingredients that would eventually go on to build planets, oceans, and biology. Their fierce ultraviolet light also began stripping electrons back off the surrounding neutral hydrogen gas, a process called reionization, which gradually transformed the universe from a vast, light-absorbing fog back into the transparent cosmos we see today. No telescope has ever directly observed one of these first stars. They're simply too distant, too faint, and their light has been stretched so far into the infrared by cosmic expansion that even our best instruments struggle to catch it. Much of what we know about them comes from simulations grounded in known physics, combined with indirect clues, like the chemical fingerprints left behind in the very oldest, most metal-poor stars still surviving in the outskirts of our own galaxy today. The James Webb Space Telescope has begun pushing closer than ever before, glimpsing galaxies from when the universe was only a few 100 million years old. But the very first generation of stars themselves remains, for now, an inference rather than a direct observation, a confident extrapolation built from physics we trust, applied to conditions we can't yet directly see. The architect nobody has caught on camera. We touched briefly on dark matter earlier, but it deserves a fuller look tonight because it's central to whether the broader cosmological story actually holds together, and because it's a genuinely fascinating example of scientific reasoning under uncertainty. The first hint came in the 1930s, when Swiss astronomer Fritz Zwicky studied a cluster of galaxies called the Coma Cluster and noticed the individual galaxies were moving far too quickly to be held together by the gravity of their visible mass alone. Decades later, American astronomer Vera Rubin studied how stars orbit within spiral galaxies and found something equally strange. Stars at the outer edges of galaxies were orbiting just as fast as stars much closer to the center, when standard gravity, accounting only for visible matter, predicted they should be moving noticeably slower, the same way outer planets orbit the sun more slowly than inner ones. The simplest explanation was that galaxies are embedded in enormous, invisible halos of additional mass, material that doesn't emit or absorb light, but still exerts gravity. Since Rubin's work, the evidence has piled up from completely independent directions. Gravitational lensing patterns that require far more mass than visible matter can supply, the detailed structure of ripples in the cosmic microwave background, which only match observations if a specific quantity of non-luminous matter is included in the model, and large-scale simulations of how galaxies cluster across the universe, which only reproduce the actual observed cosmic web when dark matter's gravitational scaffolding is built into the calculation from the start. That's an impressive convergence of evidence. But here's the honest complication. Despite decades of extraordinarily sensitive experiments, buried deep underground to shield them from cosmic radiation, and despite enormous particle collider searches, nobody has ever directly detected a dark matter particle. The leading theoretical candidate for years, a hypothetical particle called a WIMP, has been searched for extensively and, so far, has not shown up. Other candidates remain under investigation, from ultralight particles that behave more like waves to primordial black holes formed in the universe's earliest moments. A small minority of physicists have pursued an entirely different approach, proposing that perhaps there's no exotic invisible matter at all, and instead our understanding of gravity itself needs modification at very large scales, an idea known as modified Newtonian dynamics, or MOND. This alternative does reasonably well explaining individual galaxy rotation curves, but it struggles significantly to explain the lensing and large-scale clustering evidence as cleanly as dark matter does, which is why it remains a minority position rather than a serious rival to the mainstream picture. So, once again, the honest summary. The gravitational evidence for some kind of unseen mass is about as strong and as varied as evidence gets in astrophysics. What that mass actually is remains genuinely unknown, an open question sitting at the very center of the standard cosmological model, not some minor unresolved detail at its edges. The pressure pushing everything apart. If dark matter is mysterious, dark energy might be even stranger, because it doesn't just resist easy detection, it actively defies our intuitive expectations about how gravity should behave at the largest scales. For most of the 20th century, cosmologists assumed gravity would gradually be slowing the universe's expansion down, the same way gravity slows a ball thrown upward into the air. In the late 1990s, two independent research teams studying distant type Ia supernovae to measure the expansion's history found something nobody expected. The expansion wasn't slowing down at all. It was speeding up. The most distant supernovae were dimmer, and therefore farther away than they should have been if gravity alone were calling the shots. Something was pushing space apart, counteracting gravity on cosmic scales, and that something got the deliberately vague name dark energy precisely because nobody actually knows what it is. Based on the best current measurements, this mysterious ingredient makes up roughly 68% of the universe's entire energy content, dwarfing both ordinary matter and dark matter combined. One leading explanation revives an idea Einstein himself proposed and then abandoned: a cosmological constant, essentially a built-in energy inherent to empty space itself, that produces a steady outward pressure simply by existing. Famously, Einstein had originally added this term to keep his equations describing a static, unchanging universe, and after Hubble's discovery of cosmic expansion made that unnecessary, Einstein reportedly called the whole exercise his greatest blunder. It's a strange twist of history that the very term he regretted adding might turn out to describe something real after all, just for a completely different reason than he originally intended. But the cosmological constant isn't the only candidate on the table. Some physicists explore the possibility that dark energy isn't constant at all, but instead some dynamic field, sometimes called quintessence, that changes in strength as the universe evolves. Others propose that what we're calling dark energy might actually be a sign that general relativity itself needs some adjustment on the largest cosmic scales. Rather than requiring a new substance at all, upcoming missions like the Euclid Space Telescope and the Vera Rubin Observatory are specifically designed to map how dark energy's influence has changed, or hasn't changed, across billions of years of cosmic history, hoping to finally narrow down which of these competing explanations, if any, is correct. Until then, dark energy remains exactly what its name implies: a measured effect with overwhelming observational support and essentially zero confirmed explanation for what it physically is. That's not a small asterisk on the standard cosmological model. It's the single largest unexplained ingredient in the entire universe by sheer percentage, and it sits right at the heart of any honest answer to tonight's question, reaching toward a theory that doesn't exist. Yet let's circle back to that earliest moment, the one where our equations break down completely, because it's worth understanding just how seriously physicists are working to patch that hole, even though no patch has succeeded yet. The fundamental problem, as we discussed, is that general relativity and quantum mechanics have never been successfully combined into a single working theory. We need something like that combination, generally called quantum gravity, to properly describe the universe's first instant, when everything was compressed into a space small enough that quantum effects should have mattered for gravity itself, something neither of our two existing frameworks was built to handle. String theory is probably the most famous attempt at a solution. It proposes that the fundamental building blocks of reality aren't point-like particles at all, but tiny vibrating one-dimensional strings with different vibration patterns producing all the different particles and forces we observe, gravity included. In certain versions of string theory, the singularity at the beginning of time gets replaced by something gentler, like a collision between higher dimensional structures called branes, or a bounce from a previous contracting phase. The appeal is real. String theory naturally incorporates gravity at the quantum level in a way that's mathematically consistent. The problem is equally real. String theory makes very few testable predictions at energies we can actually access with current experiments, and after decades of intense theoretical work, it remains unconfirmed by any direct observational evidence. Loop quantum gravity takes a different approach, proposing that space itself is made of discrete, indivisible chunks at the smallest possible scale, rather than being smooth and continuous the way it appears at everyday scales. In several versions of this framework, The singularity at the beginning of time is replaced by a big bounce, where a previous collapsing universe reaches a minimum size, governed by quantum effects that prevent it from compressing into true infinite density, and then rebounds back outward into the expansion we observe. Like string theory, loop quantum gravity remains mathematically promising and observationally unconfirmed. There are other approaches too, ranging from causal dynamical triangulations to various models built directly out of quantum cosmology, each attempting to describe the universe's birth, not as a singular event, but as some kind of quantum transition from a prior state, one where the very concepts of before and after, in any sense we'd recognize, may not have applied at all. None of these frameworks has produced a confirmed, testable prediction that's actually been verified by observation. That's the honest state of the field right now. We have multiple serious, mathematically sophisticated candidates for what might lie beneath the Big Bang's apparent singularity and exactly zero confirmed answers. If your version of tonight's question is, do we understand what actually happened at time zero? The honest answer remains a patient, ongoing, genuinely humble, not yet. Whispers of a bigger picture, one more idea is worth including before we settle towards sleep, not because it's confirmed, but because it represents how seriously some physicists take the possibility that our universe might not be the only one. Certain versions of inflationary theory predict something called eternal inflation, where the runaway expansion that smoothed out our early universe never actually stops everywhere at once. Instead, in this picture, inflation continues forever in most places, while small pockets here and there randomly stop inflating and bubble out into ordinary expanding universes, each potentially with different physical constants, different properties, even different laws of physics entirely. Under this model, our Big Bang wouldn't be a unique, singular event at all, but simply one bubble among an enormous, perhaps infinite, number of others, forever disconnected from us by the relentless expansion happening in between. This idea, often grouped under the term multiverse, sounds like science fiction than science, and it's worth being honest about why. It currently makes essentially no testable predictions we can check with present-day instruments. Some physicists find it a natural, almost unavoidable, mathematical consequence of inflation, something that falls directly out of the same equations that already match our observational data so well. Other physicists are deeply skeptical, arguing that a theory describing universes we can never observe, even in principle, starts drifting outside the boundaries of testable science altogether, edging towards something closer to philosophy. This tension matters for tonight's question because it highlights an important distinction worth carrying with you. Not every idea floating around serious physics departments carries the same evidential weight. Cosmic expansion, the microwave background, and primordial nucleosynthesis are extensively tested, repeatedly confirmed, and about as solid as scientific claims get. Eternal inflation and the multiverse sit at the opposite end of that spectrum, mathematically motivated, genuinely interesting, but currently untestable, and therefore appropriately treated with far more caution and far less confidence. What would it even take to prove the whole thing wrong? Here's a question worth sitting with for a moment because it cuts right to the heart of what makes this scientific story trustworthy in the first place. What evidence would actually be capable of overturning the standard Big Bang picture? This matters because a theory that can't be proven wrong, even in principle, isn't really doing scientific work at all. The strength of the Big Bang model isn't that it's been declared true by authority. It's that it has made specific falsifiable predictions, and those predictions have survived decades of attempts to break them. If the cosmic microwave background hadn't existed, or had shown a dramatically different temperature pattern than predicted, the model would have been in serious trouble back in 1965. If the ratios of hydrogen to helium found in pristine ancient gas clouds had come out wildly different from what nuclear physics predicted for the early universe's conditions, the model would have failed that test decades ago. If galaxies at different distances hadn't shown the specific proportional redshift pattern Hubble and Lemaitre identified, the entire expansion picture would have collapsed before it ever got off the ground. None of those failures happened. Instead, the model kept making increasingly specific, increasingly risky predictions, and kept passing the tests again and again across nearly a century, using instruments its original founders could never have imagined. That track record of surviving repeated genuine attempts at falsification, rather than simply accumulating comfortable confirmations, is exactly what separates a robust scientific theory from a comforting story we've simply chosen to believe. That said, the model still has live, ongoing opportunities to be proven wrong, or at least substantially revised. If future, more precise measurements of the Hubble constant definitively rule out every proposed systematic error and the tension remains, that would point toward something genuinely missing in our understanding of the universe's contents or behavior. If experiments searching for dark matter particles continue coming up empty for another few decades, that would lend serious weight to alternative gravity theories currently sitting on the scientific fringe. If gravitational wave observatories ever detect a specific signature predicted by certain bouncing universe models, that could meaningfully shift the debate about what happened at the very beginning. These aren't hypothetical possibilities dreamed up for the sake of intellectual fairness. They're active research programs funded, staffed, and actively pursued by scientists hoping, in the best traditions of the field, to either confirm or genuinely break the model they've spent their careers studying. So, did it happen? Let's actually answer the question we started with, because after all that nuance, it deserves a real answer rather than a shrug. Did the universe expand from an extremely hot, dense early state, cooling and stretching over roughly 13.8 billion years into the cosmos we see today? Yes. This part of the story is supported by three independent, mutually reinforcing lines of evidence: the recession of galaxies, the cosmic microwave background, and the abundance of light elements discovered separately by different scientists using different instruments, decades apart, and all converging on the same conclusion. If any single piece of this evidence were missing, you might reasonably stay skeptical. With all three lined up together, the case is about as strong as cosmology gets. Did everything begin from a single infinitely dense point, an actual literal singularity the way the popular image suggests? We genuinely don't know, and many physicists suspect that's probably not the literal truth so much as a sign that our equations break down before reaching that point, and that some future theory of quantum gravity will replace that singularity with something more physically sensible. Perhaps a bounce, perhaps something stranger still. Do we know what triggered inflation, what came before it, or whether before is even a meaningful concept at that boundary? No, not yet. These remain some of the most actively researched open questions in all of physics, explored through mathematics, indirect observational signatures, and a great deal of careful, patient argument among people who've devoted their entire careers to chasing this exact mystery. Is the model perfect, fully explained with no loose threads? Absolutely not. The Hubble tension is unresolved. Dark matter and dark energy, which together make up the overwhelming majority of the universe's content, remain fundamentally mysterious. The lithium problem still nags at the edges of an otherwise beautiful agreement between theory and observation. And that, honestly, is what makes this such a satisfying story to fall asleep to. Not because it's perfectly tidy, but because it's real. A living, breathing scientific picture built by thousands of careful people checking each other's work across nearly a century, getting most of it remarkably right, while still leaving just enough unanswered at the edges to keep the questions alive. Real science rarely arrives at the kind of absolute closed-book certainty that makes for a tidy headline. It arrives at something better, a framework strong enough to build on, honest enough to admit what it doesn't yet know, and humble enough to keep listening when the universe offers up a number that doesn't quite fit. So, did the Big Bang happen? The honest answer, the one a careful scientist would actually give you at 2 in the morning after a few drinks at that same conference bar, is this: almost certainly, yes, in the sense that matters most. Our universe really did expand from a hot, dense early state, and that part of the story is about as solid as scientific knowledge gets. But the deepest layer of the question, the part about a true beginning, a literal 0 point, what came before, and why there was a universe at all rather than nothing, that part remains wide open, genuinely unknown, and probably will be for a long while yet. And maybe that's not a flaw in the story. Maybe that's the most honest place to rest your head tonight, knowing that the universe you're lying inside of, the one whose ancient light is quite literally drifting through your bedroom right now, has revealed enough to build an entire civilization's worth of understanding while still keeping just enough mystery in reserve to make tomorrow night's questions worth asking too. Let the room go quiet. Let your eyes close. Somewhere above you, photons older than any star are passing silently through the walls, carrying the faint, patient memory of a beginning we've measured, but never quite fully explained. And somehow, that unfinished sentence is the gentlest place of all to drift off to sleep.